Hello, Mr. Luan, are you right? Anybody tell me what did we talk about last lessons? Look at this. What's this? Do you still remember? That was like 5 days ago.
I don't remember.
You don't remember? Okay, that's fine. So we are given
yeah.
So we're given an undirected, unweighted graph, and we're also given a list of forbidden nodes, right? And then we are initially at node 0. We want to find out how many nodes we can go to without stepping on those forbidden nodes, right?
Yeah, what I'm saying.
Okay, okay.
That's what I'm saying. That's a tree.
Yeah, tree, but it could be a graph, right? It could be a graph. For example, like
Yeah, but
0,
that's a
1,
tree.
2, 3, 4. If 2 and 4 are forbidden, then at the beginning we are at 0, okay? So how many nodes? 2 nodes, 0 and 1, right? So basically we're given a graph, undirected, unweighted graph. Undirected means that, it's bidirectional, okay? Undirected means the bidirectional. Both ways, basically both ways.
Yeah, me.
So another thing is that node 0 is not in the forbidden list. Otherwise, we can simply return 0. Am I right? Okay. Node 0 is not in the forbidden list. Okay, forbidden. So we talked about depth search last lesson, right? So basically, we start at the node 0 and then we can go as deep as we can. As long as it's not visited and it's not in the forbidden list, then we can keep walking, right? We can keep walking and then we increment the counter along the path. What's another way to traverse the graph or tree? Breadth search. Can you explain breadth search in 1 or 2 sentences?
You just kind of like looking at them. Where the graph is like row by row.
Row by row. But in a graph, there's no levels. So how can you explain this? So what's the breadth search in the graph? What's the breadth search in the graph? For example,
it's like the levels. There are levels.
Levels.
Like the root is at the highest level. You know what I mean?
Yes. Okay. Interesting. So for example, here. This is node 0. This is 1, 2, 3, 4, 5, 6. Okay? And then here 7, 8.
Yeah.
So how does it work? This breadth search.
Yeah. So 0 is at the top.
Yeah, it's a root, yes.
Yeah, and then the for like
These are level 1, right?
yeah, there's a level 1 because it's like the levels of like kind of like it's hard to explain.
How do you check? How do you determine which level is this?
Determine.
Yeah, determine which level.
Determine.
Okay.
Okay, so 0 is always the root, so you always start there, and all of it's like adjacent nodes, so it's first level and then next level.
The distance, right? The straightforward explanation is that distance. We start checking the nodes at distance 1 and then distance 2, distance 3, right?
Yeah.
Explain that, okay?
That's what I'm saying.
Okay, so how can we implement the breadth search?
So
Which kind of data structure we use to implement the breadth search?
DQ.
DQQ, okay. And which data structure we use to implement the breadth search?
Stack.
Yeah, stack. Or recursion, right? When we implement using the recursion, the computer actually maintain the stack for us. And if we implement the recursion by ourselves, we can implement the stack. Actually, it's quite similar. If we change the stack to queue, and we'll get the breadth search. Okay, so today we're going to implement this using breadth search. So this part is the same, stays the same. Basically, we're given a list of edges, right? So from node A to node B. So we iterate over the edges, and then we build a graph. This is adjacent list. It's basically key value pairs, where the keys are the nodes. The value is the list of nodes that node points to. So it's bidirectional, it's undirected. Here, this is depth search. Now we need to change it to breadth search. So as you said, we're using the DQ, double NDQ. We can push and pop on both sides. So define breadth search. We given the initial root. If the root is in forbidden, which is restricted, then we simply return 0. But as I said in the beginning, the root is not going to be in the restricted list, okay? Okay, so if the root is in restricted, we return 0. Then otherwise we put it in queue, right? Queue, DQ. At the beginning, the queue is empty, but we always put the start position to the queue. So at the beginning, the queue, this is queue, right? Is the node 0. We put a 0 in, put the root in 0. Then we also need a scene table, scene hash set. We need to know why do we need a hash set to remember the nodes we have seen? Why? Why do we need something to remember what nodes we have visited?
Because like if one node is, if like one node is like is blocked off, then you can just simply ignore all of the nodes connected.
Yeah. Okay.
Next few levels. So you can just ignore those.
Yeah, but this hash set, we're using the hash set to remember the nodes we have seen. Okay, so for example, given this 0 and 1, let's consider this simple graph with two nodes. 0 points to 1. There's an edge between 0 and 1. So 0, what's the next? Keep 1. Okay, we take it out, we put it here. So what's the next? What's the kid of? What's the neighbor of the 1? 0. Yeah, and then we take it out, we put a 0, and we repeat this. We never end, right? Because we don't know, we don't remember. Bless you. We don't remember the nodes we have seen, so we keep walking forward and backwards. So we need a hash set. We need a notebook to remember the nodes we have seen. Okay, so we don't deal with the same node twice. That's basically it. Okay, because there's no point to go back to a node which you have already visited before. Alright, okay, so while queue, we have nodes in the queue. Then we take it out, right? We take it out. The current node equals queue dot pop left. We take it out from the left hand side. Queue is the first in, first out. When we want to take a node outside the queue, which side we need to take it out? Left, yeah. It's just basically the customers waiting in a line of queue. So when the next customer gets served, it's always the front, top left. When the new customers come, they're always queued at the end. It's right hand side.
The queue doesn't have to start on the left, it could start on the right.
Okay, then it's the opposite. Okay, so but traditionally, on the left, pop left. That's why we say pop left, push, pop left. Okay, we take it out from the left hand side, and then we need to check, right? We need to go through the neighbors to the nodes that it connects to. So for I in G current, right? G is the graph we have built here. Then if I not in scene, if we haven't visited this node before, also the I is not in the restricted list. Then okay, so this node I is not visited before, and also it's not in a restricted set. We push it to the right hand side, right? Q dot append. Append is to the right hand side. Append left is on the left hand side. So for the double-ended queue, if we don't specify the direction left, it's on the right. Okay. So Q dot append I, and also, we have visited this node I. We need to put it in a hash set, right? So scene dot add I. Okay, so at the end, we just need to return the size of the scene table, right? So how many nodes we have seen? So this function, breadth search, return the node, return the number of nodes we can visit from the root. Okay, so we need to return the length of the current. The scene, at the beginning, at the beginning, we have seen the root, right? So we need to initialize the hash set with the root. Every time we take one node at a time, right? So q dot append. Every time we take one node, dq, we take one node from the queue, and actually we can take everything out of the queue at once. So there are two ways. So as I said here, the breadth search, we can dq, we can take one node at a time. So every time we take a node from the left hand side, and then we push all the nodes it connects to at the right of the queue. This is one way. Another way is that we can take everything out of the queue. For example, like, this here is 0, 1, 2, 3. Then we can take everything out and then push all the kids of the next level. So we push the nodes. We push the children of the neighbor node of 0, 1, 2, or 3 at once to the queue, right? Make sense? So this is breadth-first search. We're using a double-ended queue, and then we just have to return breadth-first search as 0. Okay, what's the time space complexity?
O(n).
N is the number of the vertex. Actually, it's O. We talk about the complexity in the graph is OV plus E. V is the vertex, E is the edges, and ON. Sometimes you can say ON. N is the number of the vertex. Okay. Okay. So can you tell me what have you learned today?
Breadth search is the same problem.
Okay. What is the problem? Okay. What's the problem? What's the solution?
So the problem is we have this undirected graph
Yeah.
with some nodes which are kind of blocked off, and then you trying to see how much nodes you can cover starting from 0, and the solution we're just using breadth search, DQ, set, that sort of stuff.
Okay. That's it for today. Bye bye. Bye.
Bye.